Awesome. All right. Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. So please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Spencer Bryngelson, who is an assistant professor in the College of Computing at Georgia Tech. Previously, he was a senior postdoctoral researcher at Caltech with Tim Colonius, a visiting the researcher at MIT with Themis Sapsis, and a postdoctoral researcher at the Center for Exascale Simulation of Plasma-Coupled Combustion with Carlos Pentano and Dan Bodeny. He received his PhD and MS in theoretical and applied mechanics from the University of Illinois at Urbana-Champaign in 2017 and 2015, working with Jonathan Freud. In 2013, he received a bachelor's in science degree in both mechanical engineering and mathematics from the University of Michigan, Dearborn. Spencer won a few awards like the Young Investigator Award from Oak Ridge National Lab, the UIUC Outstanding Dissertation Award, and the UIUC Hassan Aref Award for Research in Fluid Dynamics. Today, Spencer will talk about comparative physics-informed networks, which is a very interesting topic. Please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton to Spencer by asking one random question, really random questions. The random question is, what is the most irrational superstitions you have, if you have one?
Most irrational superstition that I have. I'm not a very superstitious person.
Yeah, scientists is not
but
superstition.
I guess maybe most scientists aren't. I don't know how to answer that question.
Let me ask another question.
Okay, no,
You got it?
I have a superstitious that consciousness is not real. How about that?
Oh, okay.
How about
Right.
that? It's a weird.
Yeah.
It's a weird answer, but I think it may be a somewhat controversial one. So
I think it makes sense. Yeah. It's a perfect answer for the weird question. Okay, the stage is yours.
Thank you, Young-Soon. Okay, well, thanks everyone for having me, and thanks for the nice introduction. So physics-informed neural networks are a hot topic, as Young-Soo has alluded to. And so we're going to get down to some nitty-gritty details here about what I think is going on in this research area, and maybe some of the problems that exist and some potential solutions to them, which I understand is a bit vague, but we'll get there. First, we'll do the acknowledgements at the beginning, so I don't forget. So really, the brains behind this operation are two outstanding students, Si Zheng and Yash Kothari. They are two great students that work in my research group. I also have an outstanding collaborator, Professor Florian Schaefer, who is also in the same department as I am and is sitting a couple of offices away from me right now. So I'm very grateful for them, and they contributed to this work as well. And there's a paper that is associated with much of this work that you can refer to as you see fit. It's on the archive, and it was just accepted to iClear 2023. Okay. So let's first do just a quick overview of what the heck a physics-informed neural network is, even though maybe many people know, but we'll do a quick introduction. So the idea of a physics-informed neural network is simply that, number one, your task is that you want to solve a PDE, and the way you're going to do it is you're going to encode the solution to that PDE into a neural network. The neural network doesn't necessarily have a very complicated topology. It's in many cases just a multi-layer perceptron, though some people have experimented with different types of architectures. But at the end of the day, it's just a neural network in which you are encoding the solution to a PDE via training, and that's it. And then, so in the way that this is done is that the loss function for the training of this PDE is simply the mean squared error, so the difference between the exact solution to the PDE and the one that you observe. So this is, and so the magic of this, or the seeming magic of this, is that through back propagation, you can get all of these, you can accumulate the derivatives to any partial differential equation you may have on hand, or ordinary differential equation, such that you don't actually need to really have any data on hand. All you really need to have is the PDE, and then I can then formulate what solutions, or I can create a neural network, I train a neural network to represent its solution, which is a really clever little trick that sort of bypasses problems of, oh, well, how do I come up with so-called truth data and so on and so forth. And because of its simplicity, this is why it's so popular seemingly these days. But now I thought I'd be remiss without doing a little bit of archaeology here. So the idea of introducing physical constraints, in this case, a partial differential equation, but of course one can imagine other physical constraints, being integrated into a artificial neural network is actually a rather old idea, or at least rather old by neural network standards, artificial neural network standards, and the research in the field. So if we actually go back to 1994, Thompson and Kramer, they introduced these ideas of intermediate variables and residual modeling as a way of actually solving for models. And now they weren't necessarily solving PDEs that may have been beyond their computational capabilities at the time, but they had this very similar fundamental idea. And so that was quite interesting, and it didn't really gain tremendous traction at the time, but they had seemingly the core idea there that seems to come ever so naturally to us once you're told it, at the very least. There's also this idea of physics-based pre-processing, where you inject some prior physical knowledge, and then you train your neural network model. So you do this sort of ahead of time instead of during training. And so that also has been around for a long time, at least since 1998, if not earlier. And so humans we have this idea that if our neural network isn't really doing what we want, maybe what we can do is we can just inject some physics in some sense, or some sort of mathematical representation of that physics, and that will make things better. And so it turns out that idea is not extremely new. And we can go on and on. In 2005, folks came up with the idea of a finite element neural network, where all of the weights that compose the neural network were actually pre-computed because people had an idea of what they should be to begin with, because people have understood finite element methods for a long time. So people tried that as well and had some success. And then we go further and further, and there's some work in 2007 where people are incorporating physical models as neural network constraints, and had more and more success as more computational resources were available. So here we're looking at something like a constitutive law on the top in order to get some temperature of a material. So none of these specific applications or ideas notwithstanding, the reason that perhaps they didn't get a ton of traction is because maybe we just weren't quite ready for them, or we didn't, both in terms of sort of computational horsepower or in terms of the software tooling needed in order to make them easy to create. But it just so happens around maybe the mid-2010s that these types of tools became common. So I'm thinking of things like PyTorch and TensorFlow and so on, as well as GPUs started exploding onto the scene where now sort of everyone can have access to a GPU or a small cluster of GPUs in order to train these things. And between the two, it sort of was just the right sort of mixture of things in order to pop out these things deemed physics-informed neural networks, which is a quite similar idea, but it was just really came in at the right time and showed all sorts of great examples about what these things can do. And so this is, of course, the quite now famous paper of Verassi, Perdikaris, and George Karniadakis that I think many of us are familiar with. So PINNs pop into the scene in 2019, though the archive version of their paper was, I believe, 2017. And so since then, we've had a bit of a research explosion in this area. Basically, all of these papers in this review, so you can find this on the archive, and this is a separate paper, are purporting to try to sort of hammer away at they're attempting to hammer away at this problem in all sorts of from basically every different angle. And I think we're going to get to in this talk, we're going to get to the point of why so many of these papers exist. Why we're looking at there's references here, at least on this slide, into the 300s. So part of this is because this tool is powerful, but part of it is because it actually needs some help. So I'm going to get to that next. Okay, so this is to bring us back after this short history lesson. This is again what a physics-informed neural network looks like, and I'll recall to you that this MSE here stands for mean squared error. So this is like an L2 error on basically the difference between the solution or the residual of a PDE. So maybe you want to focus on this part where my pointer is, this F minus Laplace U. So here we're just solving a Poisson-like equation. So this is the PDE residual, and then this other term is just sitting in for the boundary conditions. Perhaps it's not especially important. But here, this thing in the loss function, which is really the main meat of what makes up a neural network, and is certainly how it is trained, is what's going on here. And so I suggest, and I hope to show some evidence, that this is actually part of the crux of what will become a problem. Okay, so the problem here is that these physics-informed neural networks, if I give them a PDE, if I give them the Navier-Stokes equations, if I give it even seemingly sometimes quite benign PDEs, or even ODEs, then it will struggle to come up with a accurate representation for the solution. It will, and what I mean by that is essentially that the loss function will actually not decrease to a very low level. So here we're thinking about something on the order of like 1% L2 error. And of course, it can be much worse than this. There are some cases where some PDEs just do not train at all. So you start off with some error and then basically nothing happens as you go through training. And this is well documented. I put some example papers here. There's probably been even more since I first created this slide like a couple of months ago. So this is well documented. And the question is, well, what's going on here? Why can't I train my neural network, my PINN, to represent this PDE? Wouldn't it be so great if I could? And it turns out that, and it's not really clear what the reason is, because it sometimes sort of butts its head into seemingly benign PDEs, whereas for a more complicated looking PDE, everything is just fine. And you get all sorts, and the training error is quite low, and everyone's happy. So the question is, what is going on here? So how do we fix this thing? And I hope to talk about that next. Okay, so my suspicion here, which I hope to convince you of, is that the main cause of this problem is that these problems are poorly conditioned. So the PINN loss function is this L2-like error, or this squared error involving differential operators. Of course, they can be of higher differential order, which would only make the problem worse. And so, but then at the end of the day, the problem we're actually trying to solve, so if we just think about this in the context of a discretized linear problem, a discretized linear differential operator, so something, again, seemingly benign, in this case, a Poisson equation, then this is the problem that you're trying to solve here, right? And so we know that this is the solution to this minimization problem, and if you put this thing through gradient descent, this is going to be essentially what gets computed and the problem that tries to get solved. Now, and you're solving here for you, that's the solution field that you want, and you can have once you actually have that thing, you can evaluate it anywhere in, say, space, or if this was time dependent, you could evaluate it in time, and so on and so forth. But if we remember our numerical linear algebra, we see that there's something quite nasty about this problem, which is that this A transpose A inverse is actually a quite nasty thing. This is akin to solving the normal equations for a linear system, which squares the condition number of that operator. So if A is encoding any differential information, we are now squaring that condition number, which is something that we all learned that we don't want to do sometime during our schooling. And so this is essentially what's happening every step through evaluating the loss and doing your gradient descent, or however you would like to optimize your neural network, your PINN. Okay, so this seems to be a key problem to what's going on. And so instead, a way to fix this partially is to get rid of this L2 type business. But the problem is that you don't really want to give up this L2 type property because it has this nice convexity properties, and L2 is nice for all sorts of other reasons. So you don't really want to leave the L2 space. And instead, you'd like to solve this in perhaps a different way. And so this is where I think a reformulation of otherwise the same problem is beneficial. And so here we are recasting the same problem as instead a minimax minimization problem. So a minimax solution to the same problem. So here we are minimizing now the solution to this PDE, where here pi steps in as the solution. So this is still the PDE residual in the parentheses. And then D serves as something that looks like a discriminator that is imposing penalties onto this thing. And so this is a so-called mini-max problem where the D is trying to penalize solutions that are is trying to penalize mistakes that are made by the approximation pi, and vice versa. Pi is trying to minimize the term that are in parentheses such that this is small. And so this is a back and forth game that is going on between these two agents. And so if you recast this minimax game into its linear formulation, which is what's shown here, then it turns out that the condition number of this linear system has the same condition number as the original derivative operator, and so things are better posed. And so that can save quite a bit of heartache, and I hope to show you some examples about why that are compelling, that suggest that this is important. Okay, so the next question is that we need to implement this thing. So we have here this mini-max game in the top left. Here's our PDE residual for our sort of toy PDE, our Poisson problem. And we have our discriminator hanging out here. And this is what the architecture looks like. So now we have two multi-layer perceptrons in this case. One serves as a neural network representing the discriminator, and the other serves as what is our good friend, the PINN, that is going to give us the solution, in this case, pi. But otherwise, they're up to the same business, except that they are now competing. But now we see that the loss function looks a little bit different. We have products here, for example, between D, the discriminator, and the residual between the residual of the PDE that we hope to solve. So we see that this no longer looks like an L2 type mean squared loss function. This looks different. So that's what the architecture looks like. And now The next question is, how does one actually go about optimizing such a type of game between this discriminator and this PINN network? And so that's where this idea of competitive optimization comes in. So it turns out that this is a quite necessary task, and I'll make the argument for that in a moment. But what one can imagine in this CPINN instance, that's what we call it, these competitive pins, is that the discriminator is acting as one agent that is trying to do what's in its best interest, which is to penalize the mistakes of mismatching the solution to the PDE. And the Y is the actual PDE residual, which is trying to be as small as possible. So this X and Y, these two agents, X and Y, are in competition with each other. Okay, and so one can think about this as sort of like a cat and a mouse, where the mouse is this agent X and the Y is the cat. And they're each hoping to minimize their respective loss functions F and G, because the cat wants to get the mouse and the mouse does not want to be gotten by the cat. So the thing to notice here is that the loss of each of these, the F's and the G's, depends on what the other one does. And so it turns out that this is rather important. So what the cat does, or what the mouse does, influences what the cat should do next, and vice versa. So, and this can go back and forth, actually, if you think about this in sort of finite time steps. This can go back and forth sort of infinitely many times, like what would I do if he knew what I was going to do, and back and forth and back and forth and back and forth until you reach an equilibrium. Okay, but we're going to get to that a little bit more in a moment. But I'd like to get into just a little bit more detail here because I think it's helpful. So one thing to notice here is that these two agents, they have conflicting goals. So what is good for the mouse is bad for the cat, and vice versa, which is shown here as they are basically, in essence, opposite types of loss functions, which again are akin to our CPINNs instance. And so one way of viewing this is, okay, well, why can't I just do my regular gradient descent type of algorithms or something like them in order to solve this problem? So let's look at what regular gradient descent, or what I like to call simultaneous gradient descent, looks like for such a problem with two agents. So here we have the update on X and on the left, and the update on Y on the right. And so what you see is that what the X will do only depends on what the Y did at the previous step. So basically the update only depends on Y at the previous step, and vice versa. Y only depends on what X did at the previous step. Okay, and so we can see that if one actually goes through with this strategy that's embodied in these two little equations, that this strategy actually diverges even on quite simple examples. So if the loss function of F, the agent F, is just this inner product between X and Y, which happens to be at odds with the loss function of G. So let's just define this. So there's like a triple equality here as minus G, because they want to do opposite things. They have opposite objectives. Then this thing even diverges here. And so that's what's shown in the picture, where here basically the state of the agent X and the agent Y is plotted on this two-dimensional axis. So that makes up one circle here. And then the arrow represents the direction that basically the loss functions are pointing you in. But we see that this basically diverges in this spiral-like fashion, and the reason for that is because, for example, if agent F were to play for example, in rock, paper, scissors, if the agent F were to play rock, then the agent Y would know then next to pick paper. And then after agent F observes that agent Y or G picked paper, it would then pick scissor, and back and forth and back and forth and back and forth. And not only would you not converge, but you would actually diverge in this sort of spiral-like fashion. So this type of typical gradient descent does not work on these types of game formulations that I've laid out in the previous slides. Okay, so then the question is, how does one linearize a game such that we can get some type of gradient descent-like algorithm, because we know they are useful, in order to carry out this optimization in a way that doesn't have these nasty properties, and perhaps one that's even kind of good. So one idea is to just have one agent, and where the optimal strategy is just the regularized linear local approximation of what it should be doing. And the other is to have two agents where the optimal strategies are linearized local approximations for both of the agents. But then the question remains, how do you actually linearize in order to deal with these problems? And so I'm going to briefly go through the math of how these terms show up, and hopefully that makes things a bit more interactive here and more interesting. And so here, let's look at what is basically essentially straightforward gradient descent on the update to agent X and the update to agent Y on the top and bottom respectively. And so here, what we see is that if this is linear for one agent, then it is actually linear for two agents. So this is just the gradient. What you're looking at the top is just the gradient descent update for so how X should change. And here, this is just sort of the truncated Taylor series. So you have the argmin of the objective function f, and then you have your gradient terms in X and Y that show up, evaluated, of course, at X sub k, Y sub k. And then you have this regularization term that basically enforces or penalizes good or bad behavior, which looks like this inner product term. So this sort of corresponds to how big of a step you would take given the confidence that you have in your objective function. And the same thing is on the bottom, except now we're looking at G's instead of F's, and we're looking at Y's instead of X's. But otherwise, things are the same. And we still end up with these two terms showing up here, except again with the G. Okay, and so I think the interesting part that will come up here is that if you do this with sort of normal gradient descent, then and you linearize this problem, what you will find is that all of these cross terms, the terms that perspective that potentially could give the information about what the cat should do, knowing what the mouse would do, and what the mouse should do, knowing what the cat should do, are actually vanish, because this term does not depend on y, and then this term is evaluated such that is not evaluated at any, this derivative vanishes because it's constant with respect to x, and vice versa here. So this term ends up being a constant, it goes away, this derivative with respect to x goes away, and so the only terms that you hold on to are the normalization terms, of course, and then these highlighted terms that are basically what we already went through. They're the terms that say, okay, well, I'm the cat, so I know that I should be doing such and such, but it's not taking in this intrinsic missing information about what the cat would do, knowing what the mouse would do, and vice versa. There's no sort of cross terms that exist here. So this actually just turns into, and the same goes for the mouse on the bottom. And so this just turns into simultaneous gradient descent once again. But then the interesting part is that there's no reason, there's actually additional terms that could be kept that are linear here. So the additional terms are these cross derivatives, in this case dxy of the second derivative operator that are shown in the middle here. And these represent what the cat would do, knowing what the mouse would do, and vice versa, and they show up in both the top and the bottom terms. One thing to notice here is that even though this represents a Hessian, it only represents the off-diagonal terms. So and so this is still linear. It is not nonlinear, and it doesn't result in any other nasty second-order derivatives. Okay, and so this allows them basically both to peek at each other and go back and forth in order to make basically the best update. And now, and so this is an interactive type of procedure. Now there's only one step left in this business, which is to find the Nash equilibrium, which is that if I know that you know that I know that you know, about the steps that I'm going to make next, then you can iterate this over and over and over again to find the Nash equilibrium where it no longer makes sense for me to move in a certain direction because knowing what you would do next, I would do nothing different, and vice versa. In this case, both players are satisfied with their positions, and then you make an update. And so it turns out that you can just get this from a truncated LU decomposition and taking that to an infinite power, and then you get the Nash equilibrium. And so this thing serves as the new update rule that makes up the basis of CGD, or competitive gradient descent. So this is just the thing that serves as our new update rule. And we argue that this is a natural generalization of gradient descent to multiple agents without bearing undue computational costs or anything nasty like that. Okay, so that's how we actually go about our optimization procedure, and that it turns out that the Nash equilibrium of this game actually is the exact solution to the PDE. So there's actually no conflict there. That's actually a nice mathematical fact that can be proved. Okay, so how does this thing perform? I purport that this is such a nice idea or something that I guess I should show some evidence that it has some nice features. So here what we do is we count the number of forward passes instead of the number of epochs, because in the CPINNs procedure, one has to account for this Hessian vector product, which is associated with these cross terms that I mentioned that make CGD what it is instead of just simultaneous gradient descent. So instead, in order to fairly take into account the computational cost, we count the number of forward passes as opposed to the number of epochs. And then we plot that against the L2 relative error, which is nominally what you actually care about. And we see that even on a 2D Poisson problem, a nice smooth one, nothing particularly nasty about it, over about 1, 2, 3, like 4 orders of magnitude, the PINN instance, the traditional PINN trained with regular gradient descent here, with Atom basically, with its special update rule, has decreased by less than an order of magnitude over all of those forward passes in terms of L2 relative error, whereas the CPINN is able to get down to single precision error. So this is carried out on single precision hardware, so this is actually as good as we can hope to do, and it does it in an efficient way as well. So, so it works here nicely. And then the other argument that one may be thinking about making is along the lines of, well, what about you're saying you're using Atom? Well, maybe I should just be using some other special optimizer, and that will take care of the problem. And we actually did an ablation study on a whole slew of different algorithms, both the most popular ones and other ones that more modern ones that people argue for. And we found that this red curve, which is the one that I presented before, called ACGD, where the A isn't particularly important, but the point is that it outperforms in a quite meaningful way all of these other optimizers, which is great. And I also mentioned the difference between forward passes and epochs or iterations. So you see, if we actually just take into account iterations, then our method here in red looks even better. But I think that's a bit of an unfair way of thinking about it. But I put it there just for reference. Okay, I have one more slide, I think. And it's on Navier-Stokes. So there's been all sorts of efforts on trying to train Navier-Stokes and all sorts of papers just about training pins on Navier-Stokes. And so we thought we would give it a go. And so my argument here is that over all of these orders of magnitude of forward passes, basically the PINN is not training at all. So this is being trained on to solve a steady cavity flow problem, a lid-driven cavity flow problem. And it decreases in relative error by like a factor of like 2 over all of these forward iterations, the physics-informed neural network with Atom. And to be clear, again, I'm only showing the best results for the physics-informed neural networks for the various optimizers. I'm not showing the ones that do worse. But for the CPINN, we do get convergence. It's a bit noisy, which I have some ideas about why that may be, but suffice it to say that it does seem to be converging, albeit quite slowly. So this requires a bit more attention about what could be going on here, but it has some similar characteristics. Okay, so that's basically the end of my talk, and I hope I left enough time for questions. The key takeaways here is that there's a training problem that is associated with this squared loss function, and that remedying the squared loss function is not maybe as trivial as it seems, and it involves sort of actually changing the architecture of how one goes about solving this problem and using sort of a little bit more specialized optimization methods. There are a bunch of good results that we have for other equations that I wouldn't burden you with showing you solutions for the Burger's equation, Schrodinger, Allen-Kahn equation, so on and so forth. So we do quite well for those as well. And the Navier-Stokes also does well, but needs a bit more attention that we're looking into. So the code for this is openly available under MIT license. You're welcome to have it and play around with it if you see fit. So I'd like to thank you for your time and for the invitation. I hope this was in any way interesting, and I am of course happy to take your questions.
Thank you so much for the wonderful talk, Spencer. Very informative and easy to follow, in my opinion. And also there were like tons of discussions in the chat room, which I can follow every single thing. But let's do this in Q&A session. Let's give the chance to ask questions in verbally. Hopefully their sound works. Let's start with Mark Miller. If you're okay to unmute yourself and ask your question directly, that would be wonderful.
Sure. Maybe I'll just ask the last one. Great talk. I wasn't able to follow all of it, but I really enjoyed it. So I had a silly question here towards the end. What do you have a sense of maybe what the total flop count is for solutions via CPINN versus traditional numerical solutions of the same quality?
Yeah, good question. So we try to take that into account with our business of forward passes versus iterations here. So actually what's going into this forward pass computation is we aren't taking into account per se the exact flop count, because that could become a bit more complicated. One thinks about that people are doing, you would nominally do this on GPUs. So I'm not sure that flop count per se is the perfect metric, but instead what we do is we just take into account the nominal number of sort of operations that are required in order to do the Hessian vector product, which is the main thing that actually changes the cost between the regular PIN and the CPINN. So that's the main difference, and that is the thing that we add to the cost, which gives this difference between the plot on the left and the plot on the right in terms of shifting this red curve to the right, as well as the yellow curve. That's somewhat less important.
I think Mark is talking about the traditional numerical method, like the finite element, finite difference, by the way.
Oh, are you talking, oh, sorry, if you're...
Yeah, thank you.
I'm sorry. I totally misunderstood your question.
No problem.
It's one I totally get all the time, so I can, the question then is, if I understand correctly, is, well, what if I want to just solve the same problem using a finite element method to solve the PDE in the same way? So I totally sympathize with everyone that wants to do this, and I actually suggest you do it. If you have a traditional solver to solve via finite elements or something, your 2D Poisson equation, and you're happy with that, it will actually be much faster to deal with that than to deal with training a PIN and solving it that way. Not only will you get smaller errors in your traditional solver, but you will solve it faster. Now, what I sort of hit here, and maybe I shouldn't have, is that the real value in these PINNs things, in my view, and maybe other people have other views, but the main value is that these things are useful for many query problems. Many query meaning that I can train this PIN to also be parametric. So you can imagine the flow over an airfoil, and then I train this PIN on a whole bunch of PDEs where the parameter is, say, the angle of attack. And now I can probe that thing as basically for free because the thing is represented as this small, compact, nice little neural network. But if you want to solve a million finite element, solve the finite element equations a million times for different angles of attack, then I would argue that that's not really a very fruitful way to go. And the more promising area here is these many query problems.
Super. Thanks so much. Really enjoyed it.
Thank you.
Thank you. Let's go to Majid. Majid, do you?
Hello, can you hear me?
Yep.
Yeah, yeah.
So I didn't actually write any questions in the chat, but I can ask a question if that's okay.
Yep.
Yeah, go ahead, go ahead.
Yeah, thanks for a great talk, actually. I mean, this study feels a little bit different from many other applications, so it's nice to get to the root of the problem with PINNs. My question is, the problems that you showed here, like the 2D problems, I'm just wondering, do you think finding the best optimizer will solve all the problems with PINNs, or using neural networks to solve PDEs? For instance, for, let's say, problems that they have time component or 3D, or where they have high frequencies and things like that. Yeah, I guess my question is like, I see there can be one problem with optimization, right? And there can be one problem with neural network not being expressive enough to solve every kind of PDEs that we deal with. So just wondering about your comments, like your thoughts on that.
Okay, yes, thank you for your question. I think I understand it. So so there's a couple things. First, number one, I should say I don't purport, and I hope I didn't give the impression that that we're somehow solving every PINN problem that exists. Just maybe a couple of the ones that people have been noticing often, and that seem to be important to getting to the bottom of some of these other things. So that's the deal with this conditioning that can be solved via a minimax type of architecture and then a competitive optimizer. So that can be what's solved there. Now, regarding your sort of other questions, whether one is thinking about higher dimensional problems. So the part of the reason I actually didn't show higher dimensional problems is that higher dimensional problems are actually easier for a PINN-like thing, or really any type of neural network type architecture, because they don't suffer from the curse of dimensionality in the same way that a traditional solver would. So if you had, for example, and a lot of people do this, and perhaps it's a bit unfair for them to do so, but point is that as you go to higher and higher dimensions, so if I think of like the 10D Poisson problem, all of a sudden a neural network type solution for that problem actually looks very, very competitive compared to any type of traditional solution to that problem, because as the expressivity of the neural network remains intact, but the expressivity, or the amount of operations that one would have to do to solve this in a sort of normal numerical methods way does not, and it scales to the power of that dimension. So that's a nasty problem, and actually that's another place. Maybe if I were to add another bullet point down here to this slide, it would be also useful for many dimensional problems. And so if those are interest to you, then things like these types of neural network expressivity things are quite attractive. The other point you made was just regarding expressivity in terms of what if my solution to my PDE has, let's say, some really nasty features, some highly oscillatory features or something like that. Does the neural network have enough expressivity in order to accommodate for those kinds of solutions? At least if I'm understanding the point correctly.
Exactly.
And I think so. There's a couple of things. One is that there's this idea of that neural networks serve as universal approximators. So which I think in many cases is used as a bit of a red herring. But the point is that but the point is still true, is that for a sufficiently deep and wide neural network, any type of solution can be expressed. So that is true. And now what, in more practical terms, if one had a really nasty equation, how big would the neural network have to be, and would it be worth making a neural network that large in order to get that kind of expressivity is a question that I'm not really prepared to answer, but it would, in some limit, it would be able to do so.
Interesting. Thank you. Thank you for your comments. Great talk.
Thank you.
Okay, thank you. Let's move on to Ripeng. I know he just commented on it, but let's give him a chance. Ripeng.
Yes. Thank you. If I can ask some questions. This is a very great talk. I'm very interested in this topic. I think my first question is actually on the slide you are showing here. I think at the very beginning of your talk you said some good features of PINN because you don't need the much data and you have some information in the back propagation. I think I didn't hear that very well. Can you please comment on that again?
Absolutely, yeah. So this comes down to the crux of what a PINN actually is, which is the idea that what I want to do is I want to solve a PDE. So what I'm showing here is a toy PDE, a Poisson problem. So I have the Laplacian of u equals f. And so I'm just basically sticking this thing into the loss function, or the error, the mismatch, the mismatch in the residual, basically, is going into the loss function. And these are just the first term here is just associated with boundary conditions. So maybe we can forget that for the moment. So that's the idea of a PINN. And then the reason that this all sort of works out nicely is because one doesn't need any data because one can obtain these derivatives. So in this case, I need the second derivatives with respect to the independent variable operating on u in order to compute the Laplacian, right? But the thing is, through backpropagation, I can just basically do autograd to get all of those derivatives for free. So this comes to the case where I don't actually need some sort of data or anything. I can automatically compute what those derivatives should be, and I can just stick them into the loss function. So I'm basically backpropagating through the neural network to compute what the derivatives are. So in that sense, you can approximate, or you can put any sort of PDE into this thing.
Gotcha. Thank you. My second question is, I think you showed one of the problem in not achieving high accuracy in PINN is the loss function. So because we monitor this residual, yeah, especially in this linear algebra sense, AU equals to F. I think a lot of traditional methods like GMRES is also a minimization problem based on the residual norm. Doesn't seem it's too much a problem for Krylov method or other traditional numerical method, but it seems like the conditioning is really a pain in this context. Do you have comments on that?
Yes, right. So good point. So one can argue about whether or not this problem of this sort of squared condition number is pervasive to all minimizers, or whether one can just somehow pick a better minimizer and be okay. Part of the thing here is that and that's part of the limitations of this linear algebra example, is that it is just a linear algebra example, and if one wanted to do this on the actual sort of through the neural network, then something like a Krylov subspace method would not be appropriate, and GMRES would suffer in the same way. So basically, the only way, as far as I'm aware, to get around this is to give away the p equals 2 norm, to give away any p even norm, and to settle with like a p1 norm. But that has its own problems to settle for an odd norm. That would be a solution, but I think it comes with other problems that I think would not be conducive to the type of things that people usually care about.
Okay, all right. Thank you.
Thank you.
Okay, thank you. Let's move on to John Ragusa. We're giving you a chance to ask a question, John.
Hey, thank you. Great talk. I liked it a lot. Very interested in PINNs. I also have lots of issues with PINN, so maybe I'll send you an email later. But let me just ask a couple of questions if there's time. Have you tried cases where the PDE has greatly varying coefficients? Let's say, for example, as in a heat conduction problem, but you have conductivities in different materials, and the conductivities maybe vary by factor, let's say 1,000. So really severely heterogeneous cases. The PINNs approach seems to always find solutions that are overly too diffusive and they don't have sharp gradients. I'd be interested to know what you think of those more real life situations with heterogeneous problems.
Yeah, if you have a problem that you can't normalize the scale, so I guess you have these nasty sort of rough coefficients that you're talking about, then so no, well, the quick answer is no, I haven't tried it. And maybe I should. Whether or not I suspect that something like what I presented is somehow a cure to that or not, I don't know. I mean, like your comment about the fact that your PINN result gives on this type of highly heterogeneous problem gives a, say, overly diffusive solution or something like this. It's not, I guess one would first have to know what to really attribute that problem to, which can be a challenge, but I mean, it's not clear to me immediately whether that's due to maybe whether or not the PINN has been sufficiently trained, and so the loss function is sufficiently low. Because another thing that is at least intellectually interesting about PINNs is that they can come up with solutions to PDEs because there's no data involved, right? So they can come up with solutions to PDEs that are also that are solutions, but they just aren't the one that you were thinking you would get. So people have actually used this to like show that maybe you can actually get like non-unique solutions to things like the Navier-Stokes equations. So actually some recent papers on the Millennium Prize type problems for Navier-Stokes have touched upon that. So that's another possibility. But unfortunately, I can't really speak much more to the type of problem you're talking about.
No worries. I think I'll send you an email later today or maybe this weekend. I'll tell you a few things about what I'm doing and what the issues I'm having. Now I have another quick question, if Young-Soo allows me. Is it okay,
Yeah.
Young-Soo?
It's gotta be quick.
Okay, very, very quick. What do you think of training the new generation of graduate students on those tools? Should they also learn traditional methods, or is this going to be a thing of the past? I'm just curious what your opinion is on this.
Training them to do what? To do these kinds of neural network type things, you mean?
Yeah. Maybe there will be an emphasis on learning, finite elements, finite difference type of schemes, or what we call traditional methods. What do you think? Will this take over? Is there room for both techniques? Or is there some tension in between the two? What's your opinion?
I think people are trying these things partially because they're trendy and partially because they've run out of other options. But of course, yes, young folks coming into grad school want to try the trendy things. That has always been the case, and PINNs is definitely not the first example of that. And sometimes these things prove to stand sort of the test of time, so to speak. And sometimes they do not. So I guess I don't claim to have any more clairvoyance than that. But I do think that I mean the only thing I think is that anything that involves not thinking about the math behind these things in some sort of careful way is very risky, because you end up in this situation where your results may not be good and you have no way to reason about why they aren't good. And so if you don't understand the math, then you're really out of luck, because the neural network also is opaque. So it doesn't offer you some other information in which you can sort of inform your priors and make a better choice about a model or a differential equation or something like that.
Yeah, thank you so much.
Thank you.
All right. Thank you. Let's move on to Henry. Henry, are you there?
Oh, hi. Hi, I'm here. Can you hear me?
Yeah. You can
Okay.
ask questions.
Oh, sure. Hi. Yeah, thank you. Thank you for the talk. I just wonder, so you use the PD residual as your loss function that you want to minimize in your problem. So I was just wondering, what are your thoughts on, like, does it make sense to use like a physics-based functional, like for example, like for diffusion equation, you can define the thermal dissipation functional, and then you can just minimize that to get your solution for a diffusion equation. Like, what are your thoughts on using that as your loss function?
Right. So a PINN in this context at least only purports to be solving a PDE that is prescribed. And now what you're, I think, alluding to is the idea of adding additional terms that are associated with the physics that may also be relevant. And so one can, of course, pile on these sort of additional constraints and terms in soft terms into the loss function in the hopes of getting a better result. But then it's just a matter of what do you consider a better result? If what people have been playing around with this idea, if I go back to here, what basically there's whole spaces here where people are thinking about physics guided loss functions, right? All the way down here. So all of these papers are thinking about how do I add things that are relevant to the physics that are maybe aside from just the PDE. And if there's one thing that I've learned, it's that these things are a bit, how to say, I think they kind of miss the point that if the neural network is behaving appropriately and in a way that you expect, then you don't need these things. And so in a sense, they're kind of stopgap sort of solutions to get something that looks kind of how you want it to look. But otherwise, if it's not giving you the solution that you expect, then maybe there's something more interesting going on, which is what we found. And I think that's actually why the things that are shown in the slides here have gone sort of unnoticed for so long, because people were thinking about these other types of things and not just thinking about like what is like the actual math going on in this thing.
Okay. Oh, thanks.
Thank you.
Okay, let's move to Walid. Are you there?
Yes, thank you for the opportunity and thank you for the great presentation. I'm really glad that someone is finally addressing the loss functions and the optimization issues associated with PINNs. My first question is in regards to the boundary conditions you're using for the Poisson's equation. If you can describe them briefly.
I believe that we just did periodic. No, I think no, sorry, just Dirichlet boundary conditions. If I remember correctly on that problem.
It would be interesting to see if you can use some Newman boundary conditions with sources and sinks, because that could be a very challenging problem. My second question is in regards to mixing other types of losses in the loss function. So if you had some data, so you have a different type of, let's say, a mean square error with the min-max loss function. Is that something that's possible?
Yes, it's certainly possible, either a priori or a posteriori. I mean, that's the other part of what was actually inside of the paper here. Yes, you certainly can add these other data constraints. So if you know that the data is whatever it is, then you can add it to perhaps do better here in terms of your training and get a better result. The only concern that I sometimes have about mixing and matching these two things is that the data comes with its own uncertainties, and whether or not the data is behaving exactly as the PDE that you stick in this loss function may not be always clear. So whether or not it's obeying the exact, incompressible Navier-Stokes or something to this effect is not always obvious. And if that is the case, then you could end up with this sort of tension between these two different types of loss function that may not give the results you expect. But that's like a PINN thing, not necessarily something specific to the type of architecture that I was talking about.
All right, thank you very much. Thanks. Great talk, by the way.
Thank you.
Okay, John Durgona, are you there? Oh, maybe he's not there. But he left the chat in the chat. Great talk. Can you please share the paper and the code in the chat? Yeah. So.
Well, someone can. I don't have access to the chat at the moment, but they're here, and if this is recorded, then they'll be available. They're also just on my website. So.
Yeah. All right. Sounds good. Feiju, are you there?
Oh, just a very generic question. So, can this idea of min-max mapping this to a min-max problem be applied to generic regression problems?
Can it be applied to what?
Regression problem.
Sorry, say it again.
Regression?
Oh, general regression problems. Yes. Yes, it can. It's just that I'm not sure the benefits are so obvious. It depends on what kind of regression problem you have. But if if the regression problem is solving has the same types of poor conditioning, then one can certainly reformulate this sort of loss function this way. And so there's many applications of this type of competitive tension that are useful, and one can find them in the papers that are referenced in our paper, of which there are many, and you can have a look and see there really are quite a few. I just didn't have time to talk about all of them.
All right. Thank you. Sapir, are you there? He's not there. All right. So that's all I have from the chat. But is there anyone who wants to ask questions? Unmute yourself and do so.
Can I ask a quick question?
Yeah, go ahead.
Yeah, this is Andrew Gillette. I really enjoyed your talk. Thank you. I'm curious, there's some work that was like gradient informed PINN where they do slightly better than PINN results by incorporating gradient information. Have you compared your work to that? And if so, how did it compare?
No, we didn't. We compared our work to many different, what I would call training tricks, where one adds basically one's trying to accelerate training or somehow ameliorate these costs that show up in order to get better results. And so there's a whole sort of alphabet soup of different PINN methods. And so it's true that I think these gradient things do give better results. There's I guess two things I would note. The first is that none of them seem to my eye to actually address what is the actual problem. And so I mean, if you can get a better solution without addressing the actual problem, then I mean that's fine. But at the very least, I wanted to note it, to note that this is what is likely going on. And the other is that these many of these other sort of training tricks that one of which you're alluding to, but there are others like mini batching and all these other things. We've tried some of them because reviewers wanted to see them, but in principle they can all be just added to our method anyway. So in some sense, they're in different categories.
Makes sense. Thank you.
Thank you.
Sounds good. Well, it's 7 after 11. Spencer, thank you so much for staying with us for the extra time.
Of course. I'm glad I was able to get to some of these questions.
Wonderful. Okay, so I'm sure there are more questions, but let's wrap up here. And then, oh yeah, say hi to Sungwan. He's there.
Yes, sir. Good to meet you here. Yeah.
Yes. Hope you're having a good time at Lawrence Livermore on in your first week.
Yeah, it is his first week. Yeah.
I am having a good time here. Yeah.
Very good.
Awesome. Well, thank you, Spencer, again. Let's thank applause one more time. And yeah, I mean, I hope you will increase the collaboration with the Lawrence Livermore National Lab as well. I mean, as you do with the other national lab, right? Oak Ridge and the Sandia National Lab, right? Please consider us, okay?
Yes, it'll be my pleasure.
All right, sounds good. Okay, let me push the stop button for the recording.